Okay, so recording started, and now we start the lecture. As I said before, that the topic is one of the very interesting topics you will come across, of course, within your discipline, and of course, in all aspects of life where we will progress from now, you will notice that data security as the very core of it. Whether it's e-commerce, whether it's IoT applications, whether it's general engineering or computer science, security of data will be the core of development, the development cycle. So I will give you later on examples about the modes of operations, the cryptographic techniques, probably to be something useful for IoT sensing, for deploying services such as remote controlling cars as we drive them, remote access, and things of that sort, or even general data communications. The core of it will be data encryption, data security. So the things that we've studied, of course, we looked at the background, we looked at the security side of things, and you've looked at the informal, you saw why we want to deploy security services, whether it's to deter, prevent, detect, and correct security violations when they happen. We saw what are the security attacks, what are security mechanisms, what are the security services, and we saw many examples of passive and active attacks. I hope you are aware of all of that in time. I would like to remind you, as I scroll through the slides now, the QR code that you see here or on your notes. If you have any questions or if you want any topic to be explained again, just raise your question and I'm happy to answer that. And of course, we looked at the basic security services, authentication, access control, confidentiality, integrity, non-repudiation, data. We looked at all of that and we provided examples in the past. And then after that, of course, we focused on the important thing, which is to classify. We saw the examples here. How do we classify cryptographic systems? The first thing we said that it's based on the type of operation. Is it to transform the plain text to a ciphertext? Is it transposition? Is it substitution? So these are either. The number of keys used. Is it symmetric or asymmetric? We know that symmetric means that I'm using the same key for encryption and decryption. Therefore, I'm using the same key, which is conventional encryption. That's symmetric. Then you will have the asymmetric, which is public key encryption, meaning that I will use one key to encrypt and one key to decrypt. You'll see that in the next teaching block. And the third thing is the way in which the plain text is processed. So is it ciphertext or is it block? Sorry, is it cipher? Is it the stream cipher or is it a block cipher? Stream cipher being processing one element at a time. Block cipher is processing a block of elements at a time. So if I look at any method in which we've studied so far, and I ask you to define it, I would expect an answer revolving around these three. So what is DES? DES. So the first thing you will say is that it uses both. Before I come to this, I'll start from the bottom up. So say it's a block cipher. So this is stream or block cipher. It's a block cipher. Symmetric, which is conventional encryption method, based on both transposition and substitution. Okay, so now let's define Caesar cipher. And again, for Caesar cipher, I will say it's a stream cipher. It's a monoalphabetic using a single letter, and it uses substitution as a means of method. So before I proceed to next, I have a few questions raised on the QR code. One of them is the class test open book? The answer is it's literally only written documents, meaning that you can take a book, you can take notes, but you're not allowed to take a computer, or you're not allowed to take, even if your notes on the computer, you're not allowed to take it. No electronic equipment, but you can bring your printed notes with you. Yes, it's an open book, literally, but no electronic equipment. So only printed information can be brought with you. The second question is, I would like to know the scope of the class test and the format of the test. Is it open book, closed book, and can we take paper material for the class test? This is the same thing. Yes, you can bring printed material with you, but you cannot bring any electronic ones. It's going to be open book for printed material only. Many students have been, this is another question, many students have been isolated because of COVID, cannot do class tests. I have asked, of course, this is quite something that I don't want any of my students to be disadvantaged. Any students at the university now who are able to attend the class, they are expected to be in the class. I've asked for the list of students who are stuck at home from BUPT. Once I have that, I will do alternative arrangements for them. But as I said, I will confirm this, but I'm only working with the official document I will receive from BUPT. So that's that. Now, regarding the class, can I ask the TA to please take the names and student numbers of the students who are present in the class, please? So please do that. Another question, it says, what is Mentimeter? That's a good question. So basically, it's a way in which you can ask me questions. That's where you ask me. You take that code. It's the name of the company that does it, Mentimeter. So it's basically you raise the questions or you poll, and I will answer you immediately, as you can see now. Another question, I want to use a computer to use Menti. Please tell me the Menti code. You have the Menti code here, so I'm just going to. It's on your notes, but also just here. So here's your Menti code, the one you asked for. And you can basically use that to communicate with the course, and you can raise questions. Okay, why cannot have the class test on weekends? We have many things, working labs. No, it's a class material, and basically this is something that BUPT has given me the timetable, so we cannot work outside that, I'm afraid. We have to do that based on the timetable. Another question is, you can scan and copy URL to use the laptop. That's absolutely fine. Is a class test open book? Yeah, so that's basically all the questions I've asked so far, most of which are basically about technicality. One last one here before we move on. Can you talk more about the class test? Yes, the class test is basically covers any material which is covered in these slides. It's to test your knowledge about what you've done in the class. As I said, you can look at the class notes and basically to demonstrate your knowledge of what you've done. If you attended the classes and if you understand them, that will do. Sorry, I think it says the Menti code is wrong. I'm going to read that. Yes, you're absolutely right. It's wrong. I beg your pardon. I will correct it now. And if you give me a second. You're absolutely right. Thank you for raising this. This is not something we should do, but so the Menti code should be 6879 and then 3242. So this is the code that you should use if you want to use it. So 6879 3242. Another question here. All the notes I take is stored on my computer. Can I turn the Wi-Fi? No, you cannot. Even with the Wi-Fi off, you cannot bring a computer at all. You have to print it, bring some summary, and this is it. Is the test an open book and exam or closed book? It's open book, as I said. I repeat it many times. You can bring printed material only. You can bring a book, you can bring your notes, but not a computer, not an electronic device, even if the notes are on the device. And is the final test open book? No, the final test is not an open book. This is an exercise for the final exam. The final exam, it's not an open book. So yeah, I'm working with our colleagues to make sure that the timetabling, if there's something we can do to change it, we will change it. If not, we will continue with the timetable as it is. Okay, so now I have a confirmation that the code is right. So yes, can we bring printed slides? Yes, you can bring printed slides with you. How many questions are there in the test? There are 3 questions. Lots of these questions are basically, you cannot just copy the answer. They have some twists in them. You have to apply your knowledge. So that's why I said you can bring your notes with you. So I will assume that you're an engineer and you'll apply your knowledge. So I think I've answered enough questions about the class test and about what's expected. And what question types will be? Are there any type to write? Okay, so anything to write. So basically, the type of questions, one of them, I will ask you to, for example, encrypt something using your own name or using your serial number, something like that. So you have to demonstrate how you understand this. And in the encryption, I will ask you to do permutation, substitution, expanding or shrinking permutation, uh, maybe S-box. I will ask you to explain things if something goes wrong. So it's basically to demonstrate your knowledge. If you are in the class, if you listen to the lectures, I think you will make 100%. It's very simple, straightforward if you understand the material. Okay, so basically, as I promised, I will speak to my colleagues at BUPT. If you're too busy, I don't want you to be more busy, but I promise you, this class test, it's not just a test. It's a revision opportunity for you to make sure that you reflect your knowledge so that you don't have to do a lot of revision towards the end of the year. So that's what it is, but I will speak to my colleagues to see if we can improve that. So what's the test accounting? So basically the test, it's all the class tests will account to 5% from the final mark. The coursework is 20% and the exam is 75%. You can see that in the notes. I will stop asking, I'll stop answering questions about the class test now because we want to save the time and we want to proceed to the classification. Second. Okay, so I got the attendance sheet and I have those who attended online. Okay, so now we will go back to the classification. As I said, we can classify any encryption method into, based on rather, the type of operation, if it's substitution or transposition, number of keys, symmetric or asymmetric. We said that symmetric is conventional encryption, asymmetric is public key encryption. And then the way in which the plaintext is processed, so whether it's if it's stream cipher or block cipher. Again, before I proceed, I have a question. Attendance accounts for score? Yes, in one way or another, because I have to report, probably you will not get a reference from Queen Mary, or it will be mentioned that there was poor attendance in classes. So please make sure that you attend. And if you don't, the reference letter may say attendance was poor. It will be included as well. So that's a question that I've been asked many times. Those who attended online, I have a record of that already, so it should be fine. Okay, so let's proceed with that. And so these are the examples we looked at. We don't have to visit them again. Oh, one of the very nice things that we looked at, it's the encryption using bits, ones and zeros. And what we saw is that the XOR function is the basis of our encryption. So the XOR function is if there are two bits that you XOR them together, if they are similar, the result is 0. If they are different, the result is 1. So 0 XOR 0 is 0. 1 XOR 1 is 0 because they are similar. They are different now. 0 XOR 1 and basically the same. 1 XOR 0, the result is 1. So if the two bits are different, the result is 1. If they are similar, the result is 0. And we said that this is a function. It's encryption, it's decryption. It's the same. And to prove that, I told you that if you take a plain text, which is 1 0 1 1 1 0 1 1 1 and so on. So this is a plain text. And if you have a key, which is 0 0 1 1 1 0 1 0 1, all you have to do now is to encrypt the key with a plain text. Okay, so what we have now is if you encrypt the plain text with a key, you will see that 1 XOR 0, it's 1 because there are two different bits. The result is 1. 0 XOR 0, they are similar, so the result is 0. 1 XOR 1, again, similar, the result is 0. So anything that is similar, when you XOR them together, they will be 0. And if they are different, the result is 1. And you can see the result here. You saw that we XORed the plain text with the cipher, sorry, plain text with the key to generate the ciphertext. We can send this to the receiver, and I can prove to you it's the same function we will use if I use the same key exactly. So I will get the same key here. I will XOR it with the ciphertext. So 1 XOR 0, the result is 1. It's the opposite. You can see that 0 XOR 0, it's 0. 0 XOR 1 is 1. 0 XOR 1 is 1. And you can see the result can be XORed between ciphertext and the key to generate the plain text. So you can decrypt using the same method as long as you use the same key. Brilliant. But of course, if you're not careful, there's a problem. If the attacker has both the plain text and the ciphertext, so if I manage to get the plain text and the ciphertext, I will XOR them together to deduce the key. So 1 XOR 1, they are similar to 0. 0 XOR 0 is 0. 1 XOR 0, it's 1. 1 XOR 0 is 1. So you can see that I can do the same. If I XOR any two of them, I'll get that. If I'm an attacker, I will look for a pair of the plain text and the ciphertext to get the key. That's why we need algorithms that will protect against that. And one of the things that, because of this, and if the attacker knows the key here, then there's a problem, because if I know just that, in later sequences, I will know all this plain text because I can decipher everything. So people thought about, okay, how do I do this? And I can improve it by having a totally random key shared between the sender and the receiver. But I told you that the difficulty with that is how do you send the secure key to this receiver? There's a problem with that. And therefore, it's vulnerable because of the transmission. And I can show you an example. The example we studied before, we said that if the original message was Mr. Mustard with the candlestick in the hall, and the sender will use a random key, and the random key they used is this, PXKMV. It's random here. And then what happens is that if you encrypt using Caesar cipher, M with P, it will generate B. R with X, it will generate O. M with K, it will generate W. And this will be your ciphertext. And it's absolutely random because the key is not repeated, and this is very good. But what I would like to highlight here is that there is a problem, because if the attacker knows that you received this ciphertext and the sender is trying to send you the key, what I will do is I will hold the key and delete it, and then I will generate my own message. First, I will wonder, okay, how long is the message? So I'll get the message length. I will create a message length that I want to say. For example, I would like to say, Miss Scarlett with the knife in the library, and then I'll add a at the end because I want to match the length. And then towards that, I will say, okay, so I have the ciphertext. What key do I need? Because I know it sees a cipher. What key will I need to encrypt M into B? And I find that to be P. And then what key will I need to encrypt I to an O? And I found that to be G, and I continue that. Then this key, which I deliberately designed, you'd think it's random, but it's actually not. I designed it because I wanted to send you a different message. I will give you the key that's fake, and then when you decrypt this, you'll get my message, not the original one. So that's why we have to be very careful about the way in which we process the encryption. So yes, XOR or Caesar cipher and so on, they are simple to use, and the key is very secure because it's random. But if you're not careful in the way you design your algorithm, it's a weakness. And this tells me something. All the methods that I will mention to you, they are not perfect. But with that, you will need to make sure that you make it difficult for the attacker to break into it. And I'll tell you when we think about that. So we saw many types of attacks. We saw cryptanalysis attacks. We saw how you can break a Caesar cipher or VGNet cipher. We saw a brute force attack where we will try all the possible keys to break into a code. That's a different type of attack. And then basically the explanations, I'm not going to go through that. But one of the very important things that I mentioned here is that there's no method perfect enough to call as a perfect encryption method. Therefore, we will have to think about, okay, so when do we call a method as being safe? Okay, so the answer to that is this. We can assume it is computationally safe if both the cost and the time are too expensive for the value of what you do. So if the cost of breaking the cipher is greater than the value of the encrypted information, and if the time to break the cipher is much longer than the useful lifetime of the encrypted information. For example, if I encrypt your exams, which I do, encrypted using AES 128, which is a key with 128 bits, I know that it will take you thousands of years unless you use very sophisticated computers and you spend a lot of money, probably 100 million yuan, whatever it is, very great values. I know you will not break an exam for it. It will be too expensive for the value of the exam, but also it will take you 5 years to break it by the time you already graduated, actually. But in 3 months after the exams, I will show you all the past exam papers, including this year's one, so we can learn from it. So it's not useful. And therefore, if both the cost and the time taken to break a code, it's too long and too expensive, then we will know it's computationally safe. So that's basically what we wanted to do. Before I proceed, there are a few questions. One of these students, I said, I prefer to have live stream in the dormitory. Can I watch the stream live instead of going to the classroom? Preferably if you're in the classroom, but if you're watching it live, that's fine. And then is it, okay. Is the problem only with one-time pad? No. One-time pad is, we think it's a perfect one, but to handle a very long key is a problematic. And therefore, yes, the problem here is with one-time pad. You will see that the other algorithms we use, they don't have this problem. So for example, with DES or with AES or with many other algorithms out there, if you have the plain text and the ciphertext, you'll still not be able to produce the key. So yes, the problem is only with the one-time pad, as we explained it. Okay, so we proceeded with our lectures. I'm not going to go through this. Of course, you have to learn all of that. And then we looked at conventional encryption, and we studied DES, which is based on the Feistel algorithm from the last century. So basically, the Feistel algorithm takes a 64-bit block, processes it 16 times, number of rounds is 16, and we studied subkey generation, and we said that the encryption and decryption function is identical. The only difference between them is the way in which we feed the subkey. So when I encrypt, I will feed the subkey from subkey 0 all the way to subkey 15. Whereas for decryption, I'll start with subkey 15 all the way to subkey 0. So it's 15 rounds. That's when we start doing this. Okay, so please make sure that you pay attention to the block size, the key length, which is 56 bits here. Block size is 64 bits. Number of rounds being 16 rounds. And the details in which we studied. We said that the block size 64 bits is typically divided into two half, left, right, and left. The right one goes into the function box, and which processes that right bit together with the subkey. And then the output of that, which is also 32 bits, will be XORed with the previous left side, and that will produce your new right side. And the new left side will be the previous right side. And the process repeats 16 times. But of course, we said that there is a subkey generation. We said that the function box will include expansion permutation, which I hope you know now. We already explained that. And then you should also have, you know, that the expansion permutation will take 32 bits in to produce 48 bits out. And the 48 bits from the subkey will be XORed with it. And then this 48 bits will go to the substitution box. This substitution box will take 48 bits to produce 32 bits out without losing information. And then a permutation takes place, and you know the rest. This will be XORed with the previous left one, and so on. The details of those, please note that the substitution box for the DES, it's different from the substitution box of AES. You need to know the difference. And of course, you need to know, I could easily ask you to perform permutation using this function, which is 3, 1, 4, 2, 6, 5. What this really says is that I have a sequence 1, 2, 3, 4, 5, 6, and I'm changing that order based on this function. Or if I do expansion permutation, I will say 1, 2, 1, 2, 4, 3, 4, 3, 5, 6. I'm repeating some of them, but again, you can see that you can generate the elements or reorganize them based on those. So you need to understand it. So what's the final, there's a question here. What's the final requirement of DES? How much should we command? You need to understand the details that I've discussed. You need to understand basically the process here, encryption and decryption. You need to know the block size, key size, number of rounds. You need to know this process here. You need to know each of those. So you need to know the details of it to make sure that this is. So basically the explanations here, the S box, how it works. We explained that in the lecture in the past. You also need to know, well, subkey generation, don't worry about. Just say that there is a subkey generation and this is it. I will not expect you to do this. This is for you to, if you want to read in the book, I will not expect you to write this in the exam. Now, so I have another question here. Other encryption key can also be broken, but one-time pad always transmit the key all the time. So the one-time pad more vulnerable to message manipulation than others. This is a really good argument. So I'm going to repeat this question here. So your friend says other encryption keys can also be stolen, but one-time pad, the key will need to be always transmitted. So one-time pad, is it more vulnerable to message manipulation than others? Yes. Yes, because the key is truly random. It's always transmitted. It could be intercepted. It could be basically blocked and retransmitted after modification. And therefore, this is a weakness. But if you physically exchange the one-time pad on a USB stick with another person, it could be very, very, very safe because you already pre-computed it and you physically have that key. So that's why a lot of banks use such technique. So that will make it safe. But it's a good argument you brought into the question, by the way. Do encryption and decryption use the same S-box index? Yes, indeed. It's exactly the same procedure, whether it's encryption or decryption. The only difference that you'll have, it's 16 rounds, of course. In the encryption, I will start with K0, then K1, then K2, then K, all the way to K15. Whereas when I decrypt, I will start with K15, K14, K13, all the way to K0. So it's just the way we feed the subkey. So the S box will always be the same. So I hope this answers your question. The other question, will the S box be tested in the exam? Yes, it would. So that's basically the explanation of the S box. Of course, I will not expect you to put these numbers. Don't remember those numbers. This is random numbers I put. The S box will have proper design for the values here. I use this as an example. So don't put values. You probably can do 0, 1, 2, 3, and then all the way to 15 here. That's fine. But don't populate any of these values. You don't need to remember them. I just want you to understand the concept of this. How will the S box be tested? So if I ask you to explain the exact procedure for the S box in DES and AES, for example. So with DES, you would need to know that I'll take 6 bits, take the first and the last, use them as a reference for the row, for the column, sorry, the row it is, and then the middle bits, I will use them as a reference for the column, and you have the lecture. Whereas you will see later on the AES, it's a byte that you divide it. You take the first side into reference for the row, the second side into the column, and then it will produce another byte. So with the S box of the DES, you enter 48 bits, produce here. You have 48 bits in, 32 bits out. With AES, you have 128 bits in, 128 bits out. Actually, it's a byte to byte substitution. There is no losses or whatsoever. So I have a question here. That rotor encryption is substitution and stream at the same and symmetric? Yes. It is true. That's true about the rotor encryption. Okay, so we proceed now with basically. Then we saw that okay, DES is brilliant, it's very good, it's safe, and then we said okay, so let's look at the key length. Key length is 56 bits, and I'll show you examples that 32-bit key can be broken just like that using a very fast computer. Whereas if I use 56 bits, it could take it up to 10 hours, if not less. Meaning, if I encrypt your exam questions using DES, in 10 hours, you'll probably be able to break it and you'll find what the exam questions are. So DES is not a good way to encrypt. So that's why, and then we say, okay, if I have 128 bits, brute force attack, it will take a few million years. And we know that anything above 128 will be very safe. So people thought, okay, I will use 2 different keys, and I explained that in a lecture, to do double DES to encrypt. And the effectiveness, I told you, the attacker can easily do meet in the middle attack, where the attacker, all they have to find is plain text with the ciphertext. And what the attacker will do is encrypt the plain text 2 to the power 56 times, each time with a unique key, meaning they start all the possibilities of the key to encrypt the message. And then they will decrypt the cipher 2 to the power 56 times as well, with all the possible keys. And then they will do comparisons. So effectively, we've just done the job twice, which is 2 to the power. That means it's 2 to the power 56 time, which is about effectiveness twice. That's effectiveness of around 2 to the power 57. So instead of 10 hours, you will spend 20 hours, and that's useless, really. That's not what we want. And after that, we looked at triple DES. I'm not going to go through the details. And we found that triple DES is a good way to do it because meet in the middle attack is not possible. So triple DES is very safe as well. But triple DES uses 3 keys. It uses each time of encryption, it's 16 rounds. So 16 rounds, then change key, then 16 rounds, then change key, then 16 rounds. And all of that is just a 64-bit key block. It's very inefficient, safe but inefficient. So for that, we started looking at, since the early 2000s, we started looking at advanced encryption standard. And advanced encryption standard is based on the Ragindale algorithm. And we said that it's always 128 bits block, but the key size can be either 128 bits, 192, or 256 bits. We looked at the details and we saw how basically the first round, the key is XORed with the plaintext, and then there will be substitute byte, shift row, mixed columns, and add round key, which is another XOR. And we said there is an expand key function, expands 128 bits to derivatives of it. So every round, because there are 10 rounds here, every round will have a unique subkey. So the way we did it is that we said for the substitute byte, I will not go through the details. We said the trick is we will make things very efficient by looking at 128 bits divided into 4 words. So each word is 4 bytes. And we create a matrix. We do the same with the key. We do 4 words key into a matrix. And we said that in the first round, I just XOR this one with this one. So this, the current state, which is the plain text, with the key. And I'll get XOR this one with this byte, get this byte. XOR this byte with this byte to get this byte. So basically it will generate. And then for the substitute byte, as I said, there is S box for AES. Very simple. You divide this into 2 halves, 1 half for the reference for the row, 1 half for the column. Notice that it's 4 bits. So it's up to 15, between 0 and 15. And that's what we have all the ways. And then the output will also be a byte, and therefore we will not lose any bits. You get bytes in, you take a byte out. That's the S box. And then we have shift rows. Very simple. We said row number 0 will have 0 shift. Row number 1 will have 1 shift to the left. Row number 2 will have 2 shifts to the left. Row number 3, 3 shifts to the left. Very simple shifts. Mixed columns, we said we will do the Gaussian field 2 to the power 8. I said that if you trust what I say, it's basically a way to perform it. And we looked at the function in which it operates. Then add round key for the expanded key. Basically, just the key will be expanded and another XOR as well. And that's as much as you need to know for the expanded key. Don't worry about this. I don't expect you to explain it. So for the expanded key, that is. I don't expect you to do the expanded key, but you need to understand AES, how it works. You need to understand DES, how it works. And of course, with that, I want you to remember AES and DES and triple DES are not the only way out there. There are many other encryption methods. You can even design your own conventional encryption method. There are many, and I listed examples here. Okay, so I have a question. Is break and cipher a requirement for us, like a CISA or VisionNet? Yes, it is. And the reason is I want you to be aware of weaknesses of methods. So probably in the future, if you design a method, the first thing you need to do is to criticize it and see, okay, what are the weaknesses? So yes, you are required to know the break-in of the cipher. The other one is on page 107. We need to try 2 to the power 32 times. Computers can try 10 to the power 6 times. So why do we need 2 to the power 31 rather than? Okay, so the way you compute the number of times, this is outside the scope of this module. If you just accept that as an example, if you use a supercomputer, just accept it within these realms, otherwise we'll have to spend too much time explaining it. If you just accept that if you use a fast computer, supercomputer, breaking a 56-bit code will be very easy. Within 10 hours will be effectively broken. So accept that, please. And yeah, the calculation is outside the scope of this module. The question here I have, can you explain the meet in the middle attack again? So I will do that very quickly. Another question says, will the AES be in the test? Yes, it will be. The other question is, what's the classification of the grill? It's a block cipher, and it is symmetric. Okay, so now somebody asked about meet in the middle attack. So meet in the middle attack, if as an attacker, I have a pair of plain text and ciphertext. Say, for example, you encrypted an email, and in the email, I know the first, or a website, the first tag will be HTML, and I know that tag. And then the encrypted block that's against it, I will capture it as well. Let's suppose that. Then what I will do is I will take this block and this block. The first one that's not encrypted, the plain text, I will encrypt it using all the possible keys between 56 times zeros, all the way to 1111, meaning I will do encryption 2 to the power 56 times. So that's basically 2 to the power. So that's 2 to the power 56 times encryptions of the same plain text. And then what I will do is, because I have the ciphertext, which I know this ciphertext, it's the encryption of the plain text using 2 different keys. But I don't know key 1 and key 2. I don't know them, K1 and K2. So what I will do is I will decrypt this ciphertext using all the possible keys from 0000 all the way to 1111. So 2 to the power 56 times as well. So what I have now is 2 to the 56 possibilities of encrypted plain text and 2 to the power 56 decryptions of the same ciphertext. So we are in the middle now, somewhere between the encryption and so on. What we will do now, what will the attacker do, is make direct comparisons between the encryptions of the plain text and the decryptions of the ciphertext. And one of them will match, which is in the middle, somewhere. So basically between the encryption and the decryption. That match will tell you, at that point, you will know it's that key that you used to encrypt the plain text, and the key that you've used to decrypt the ciphertext are used between the cipher and the plain text, or vice versa, between plain text and the ciphertext. So with these comparisons, you can find both key 1 and key 2. Once you know key 1 and key 2, this is it. Everything is decrypted for you. So I just use the tag HTML with a block of it, compare this with this, and I've easily deduced the key 1 and key 2, and I can decrypt everything. So that's basically what it took me. It's the effort of 2 to the power 56 twice, instead of me trying 2 to the power 112, because it's used in 2 different keys. So that's what meet in the middle attack is. I hope this answers your question. A stream cipher. Okay, another question is here. A stream cipher will belong to substitution but not permutation? No, it could be either. You could be permutation, could be substitution, a stream cipher. It's fine. The Gorilla and Playfair are both block ciphers? Yes, they are. They are both block ciphers. So one asked the question, is decryption using key 1 of cipher equals to encryption of key 2 of the message? Yes. Basically, that's the interfacing point between the two. Once you have that match, at that point, you know that key 1 and key 2 have been used to transform the plain text into a ciphertext. Can you explain the matrix on page 128? And the other one, I'll get to that. Okay, the other question is why you said the key length is 56 bits for this at first. Then you discuss the key length in the latest slide. How many years to decrypt? Okay, so I said that 56 bits, if it's this or any other method, you will try between 000 all the way to 111. One of them will work. So if you try 2 to the power 56 times, assuming you're unlucky, you will get all the way to 1111. Of course, you'll break it before that. It will typically take in a supercomputer about 10 hours to break. In the past, in the 1970s, it was good because the computers were very slow. But as the computers became faster and faster, 56 bits is not effective at all, because if I try all the possible keys, I can break them easily. So somebody said the matrix, they wanted 118, I think it was, or 180. But I lost the question here, so let's see. So it was the matrix on page 128. Oh, I explained that before. So basically what it is that the Gaussian field, we assume that it's the way we work with the clock. So basically we will always, with the clock, we have between hours 1 and 12. And I've explained that if I add 400 hours, you will have a function that will give you a result between 1 and 12 without losing information. So here it's the same. So I have the new state. So basically the state is the matrix of your information. This is the new state. It's the special GF function of basically this matrix with your current state. And we said that we will multiply each row by each matrix by each column based on the functions here, and I've explained that. Please go back to the previous recordings to see that, because now we need to save time to be able to basically proceed to the topic of today. So I will now move on to the modes of operation. And I said that in the last lecture, I said that for the modes of operation, if we feed the same key, if I basically put a letter A here, letter A here, letter here, assuming that my block is letter A, and if I use the same cipher using the same key, then the output will always be the same. And that's a weakness, and that's called electronic codebook. So the attacker can make associations between either way. By the way, I do apologize. It seems like I've exceeded the break time. You can have a break time for 5 minutes, then we can come back at 15 minutes past 1. So let's have a break for 5 minutes.